Okay, so the long-term carbon cycle is the next topic. And the short-term carbon cycle really deals with the atmosphere and living biomass. Oops, here we go. The atmosphere, living biomass, and sedimentary organic carbon. We would call it, maybe say, organic carbon in soils and sediments. That's not organic carbon in rocks, I guess. That would be this reservoir here. But the short-term carbon cycle is really all about cycling carbon between the living biomass, dead biomass, and atmospheric CO2, essentially, right? And the last thing I said in the lecture on that, and also in the last video I recorded, is that the burial of organic carbon into sedimentary rocks represents kind of a leak in the short-term carbon cycle, a connection between the short-term carbon cycle and the long-term carbon cycle. And the long-term carbon cycle is really all about these two reservoirs here: organic carbon in sedimentary rocks because of that process, organic carbon burial, and even more specifically, it's about limestone or other carbonate rocks. And so it's really all about the inorganic side of the carbon cycle, I suppose. But yeah, it's dealing with atmospheric CO2 and these other inorganic molecules. And so we've talked about this a bunch of times throughout the semester, but CO2 and water turn into carbonic acid, right? And so this happens in the presence of rainwater that's falling through the atmosphere. It creates this low pH acidic rain. It's not the same everywhere, but rainwater is naturally acidic. When that acid, the carbonic acid specifically, reacts with silicate rocks, this is a calcium silicate, it dissolves it. It produces calcium ions, and the carbonic acid turns into the bicarbonate ion. Okay, and so both of those ions dissolved in water will be delivered to the ocean. Okay, so they're carried through streams and rivers to the ocean, where inevitably they can recombine calcium and carbonate or bicarbonate to form this mineral, calcite, or the rock type limestone, calcium carbonate. Okay, and so calcium carbonate is stable for billions of years potentially. We have carbonate rocks that are over 3 billion years old that have been preserved, believe it or not. Okay, and so this process represents turning atmospheric CO2 through chemical weathering into marine limestone, which can be preserved for long periods of time. All right, and so this process really balances the release of carbon dioxide into the ocean atmosphere system from the solid Earth. So volcanism and metamorphism both produce CO2, and that's released to the atmosphere. And so if there weren't a process to take CO2 and lock it up for long time periods, volcanism would result in just accumulation of CO2 in the atmosphere over time. Luckily, that's not what happens because we have chemical weathering, right? And so these processes, chemical weathering, the conversion of CO2 into initially carbonic acid, and then that acid reacts with rocks, turns into bicarbonate and carbonate. These processes really capture the long-term carbon cycle, and the long-term carbon cycle differs from the short-term carbon cycle in that the reservoirs are stable for long periods of time, like billions of years, but the fluxes of carbon between the reservoirs are really small. Okay, and so while I said in the last video that about 10% of atmospheric CO2 ends up turning into biomass every year, and a similar amount is turned back into CO2 through respiration, a very, very, very small amount of CO2 is consumed each year through weathering, about 0.2 petagrams compared to this 750 petagram reservoir in the atmosphere. Okay, a very, very small amount is consumed, but that reflects steady state with those solid Earth processes that I just mentioned, like volcanism and metamorphism. Those inputs to the atmosphere or ocean atmosphere system are balanced by the outputs through chemical weathering. Okay, and so this is really the long-term carbon cycle. A tiny amount comparatively anyway, a small amount of CO2 is introduced to the system every year through volcanism. That is not coming from the biosphere, right? It's coming from deep within the Earth's interior. And so if that weren't balanced in some way, it would accumulate forever. Luckily, that's not the case, right? And so a tiny amount is introduced to the ocean atmosphere system, and a tiny amount comes back out in the form of chemical weathering, which ends up producing limestone, right? And so essentially we have, in a more holistic sense, these three reservoirs, right? The atmosphere, biomass, both living and dead, and sedimentary rocks. Okay, and we have four specific processes that operate on these two carbon cycles. We have photosynthesis and respiration, taking atmospheric CO2, turning it into biomass, and then turning biomass back into atmospheric CO2. Okay, and then we have chemical weathering, taking atmospheric CO2 and turning it into sedimentary rocks through this chemical weathering process, right? The formation of carbonic acid, the reaction of that acid with rocks, liberating calcium ions and turning the carbonic acid into bicarbonate. Those two ions can go out to the ocean. Calcium can recombine with bicarbonate to form a sedimentary rock like limestone. Okay, so that is that is one flux. The corresponding flux from the solid Earth, or from from the solid Earth, essentially back into the atmosphere, is volcanism and metamorphism. And so this side of the carbon cycle, the long-term carbon cycle, the fluxes are really small, but the products, sedimentary rocks, are really stable, right? And so this process, while it operates very slowly, the reservoirs here are huge, and the residence time is extraordinarily long. The short-term carbon cycle, the fluxes are huge, right? Something like 10% of atmospheric CO2 per year it goes into biomass and comes back out. The fluxes are super large, but the residence time is really short, right? As a result, the residence time of carbon in the biosphere is something like 10 years, right? And you think about it, that makes sense. Lots of organic material is produced every year. Trees grow leaves and they drop them, and then those leaves decay. It doesn't take more than 10 years for those to go away in most instances. Even faster, you think about organic material in aquatic systems, right? Algae growing in a pond die, and they're mostly consumed within probably a few weeks, honestly. So the fluxes are really large, but the residence times are short. Here, the fluxes are very small, but the residence times are very, very long, right? So short-term carbon cycle, long-term carbon cycle. It's all about carbon moving from one reservoir to another. There is this link between biomass production and the sedimentary rock reservoir in the form of organic matter burial, and that's a really important process. If we increase organic matter burial for one reason or another, it will end up lowering atmospheric CO2 on relatively short timescales. Similarly, you could change any one of these fluxes and end up changing atmospheric CO2. And that's really the point that we're trying to make with all of this discussion, is that, the climate system is all about feedbacks, and changing any one component will cause lots and lots of other changes across the system. We gave some really simple examples of feedbacks within the carbon cycle. This is maybe the simplest, the CO2 fertilization. That is just to say that plants grow faster at higher CO2. And so if atmospheric CO2 goes up, plants grow faster and they absorb more CO2. They convert more atmospheric CO2 into biomass, resulting in a lowering of atmospheric CO2, right? So it's a negative feedback. CO2 goes up, plant growth rate goes up, CO2 goes down. Plant growth rate goes down, allowing CO2 to go up, causing plant growth rate to go up, et cetera, et cetera. It's a negative feedback. Melting permafrost is a positive feedback, to be sure, because permafrost is frozen soil. And as we discussed, frozen soil contains a lot of organic material, or soil contains a lot of organic material more generally. And if you freeze that soil, it essentially eliminates or stops respiration, right? organisms don't grow in the freezer. That's why we put food in the freezer and it stays good for a long period of time. Organisms don't grow when they're frozen, and so respiration stops, and that organic matter is just preserved. If you warm that soil back up, you melt it, and allow that organic material to be respired, it releases CO2 to the atmosphere, right? And so this is a positive feedback, right? If CO2 goes up, or the climate gets warmer for any reason, permafrost will melt, organic matter will be converted back into CO2 through respiration, causing atmospheric CO2 to increase, causing conditions to get warmer, causing more permafrost to melt, more organic matter to be respired, CO2 goes up, conditions get warmer, and on it goes. It's a positive feedback. The other two we talked about were this shelf nutrient hypothesis, and this one is just saying that if sea level goes down during glacial advance, okay, so if glaciers are growing, continental ice sheets are growing, more water is taken out of the ocean and locked up on land as ice sheets, and so sea level falls, exposing these organic rich sediments. They weather, releasing those nutrients back into the ocean, and driving productivity. And so more CO2 is consumed and converted into biomass, causing atmospheric CO2 to go down, causing conditions to get colder, ice sheets to grow, sea level to fall, exposing more organic rich sediments, further stimulating productivity and the conversion of atmosphere, ocean CO2 into biomass. Okay, and so that's another positive feedback. The one really dominant negative feedback that we talked about is the silicate weathering feedback, and this is really the most important feedback in the climate system for maintaining habitability on long time scales. Atmospheric CO2 is converted to carbonic acid. That acid reacts with silicate rocks to produce cations like calcium and magnesium, and bicarbonate, which eventually react to form limestone or dolomite. That is the long-term carbon cycle. All of the processes involved there. The CO2 dissolving into rainwater, if it's warmer, or let's say atmospheric CO2 is higher, conditions are warmer, which means it's going to rain more because warmer air holds more moisture than colder air. So it's just going to rain more in general. More CO2 is going to dissolve into the rainwater because CO2 is higher in the ambient environment. The reaction between the acid and the silicate rock will take place faster at higher temperature, which is important because that's a really slow reaction to begin with. And so at higher atmospheric CO2, you get more rain, more CO2 dissolving into it, faster reactions with rocks, and actually it turns out that carbonates are going to precipitate faster as well for a variety of reasons. But you just get a general acceleration of that silicate weathering cycle. And so when that happens, it causes atmospheric CO2 to go down, right? So higher atmospheric CO2 leads to faster silicate weathering, which draws down atmospheric CO2, leading to slower silicate weathering, allowing atmospheric CO2 to build up, accelerating silicate weathering, right? So it's a negative feedback. And as long as there's the exposure, the continuous exposure of fresh rock material, which we are assured of through plate tectonics, this process will operate. And so throughout Earth's history, this silicate weathering feedback has maintained the Earth's average surface temperature in a really narrow range, maintaining planetary habitability. And so, it's really critical to maintaining continuous temperate conditions, just continuous kind of average hospitable temperatures. It's really important that we have the right types of rocks at the surface. And it's also really important that we continue to uplift them through tectonics. Both of those are really critical. But in general, the carbon cycle is really, we're talking about three major reservoirs, right? We could say the ocean atmosphere system here, the carbon locked up in biomass, both living and dead, and sedimentary rocks, and the processes that flux the fluxes that exist in between those reservoirs.